Any idea? Okay. So basically, and dendrites is something like acts as a receptor which gets input from the external world. So and they all these things they meet together at a particular point, what is called synapse. And how closely these two neurons are connected, and this is basically they are connected at the time of synapse and how strongly they are. In order to mimic that, we have this concept of weights and what we call as synaptic weights. A neuron before that is synapse, or the input before that we call it presynaptic input, and after the synapse, a particular synapse, what we call it postsynaptic input. So this terminology will be used frequently: presynaptic and postsynaptic. And also we discuss about this signal flow graphs, and we say that, and before that we saw a particular neural model which mimics this pyramidal cell, or you can see any in general biological cell, biological neuron. And that the basic building block is nothing but a summer circuits and a base and a multiplier which is denoted by weights, and we have a activation function. So basically activation function represents is nothing but like a squashing function. So its output will be confined to 0, 1 or -1 to +1, no other and other value. Okay. And the reason is that because it is some sort of impulse, the output which travels from a neuron to another neuron through axon. And as I told you, axon is basically act like a transmission line. And to confine that particular input or the output to the other one, or to fire the another neuron, this has to be a impulsive input, which is a particular electrical signal. Then later we say that, okay, the representation of this kind of block diagram approach for the entire network will be very complicated, because we saw that one particular neuron has got this kind of representation. And when I say neural network, I use basically large number of neurons are involved in that. And if I go with this block diagram approach, it will be very difficult to draw it and visualize it. Then people went for this idea about what is called signal flow graph. So this is given by Mason. And using the signal flow graphs, basically we try to represent this neural model in a very simple structure. So here two kind of links are there. One is called synaptic link, another is called activation link, if you remember. So synaptic link is nothing but whatever the input is there, and to represent the weights we just mark an arrow in the direction where it is flowing, and the outcome is nothing but the input multiplied by this particular weight. So that is the synaptic. And like an activation function, whatever the input is there, and the activation part is labeled as an arrow and by phi dots. So output of that is nothing but phi of the input, whatever is given. Okay. And then so we'll see slide I have not started again yet. So this I'm talking from the previous class which we discussed. Okay. So this is all about, and then we discuss few scenarios. What do you mean by this architectural graph and signal flow graph equivalence? So I'll come to the slides now. Don't worry. So where we left, let me see. Models of neuron was done. We are aware of what you mean by okay. So just let me share my screen with you now. Yes. So here, so last we ended our discussion here, that this is basically whether my screen is visible now. Anybody?
Yes, sir, it is visible.
Okay. So here, this is the leftmost. You can see figure 13 is talking about the signal block diagram representation of a neuron, and the middle one, as I just told you, basically is just a representation of that in a signal flow graph. You may say that, okay, man, there's no much difference as far as complexity is concerned. So this will be very clear when we start drawing a bit complicated diagram. And then we have this something called architectural graph. So in architectural graph, most of the time when you're asked to do, You don't worry about the details of those weights, etc., activation function. We don't want. So just to represent a neuron, if we put a particular circle, just to say it's a computing unit, and we try to we indicate the number of inputs it is taking. Either it may from the input layer or from the layer previous to the given layer. And just we mark this arrow with a direction, and one final output whatever. So this is basically architectural graphs. So this we'll see. Now we'll try to see this some frequently used network architecture. So connectivity of a neural network basically is intimately related with the learning algorithm, what kind of learning algorithm you're using. Even the neurons are same, but the different learning algorithm is there, so it helps in many different way. So that may speed up the learning process, or it may have a better learning. Many things can be think of. So then there is something called single layer feed forward network. So here when I say single layer or multi-layer, what do you mean by that? Just wait for a minute, it will be clear. So in a single layer, because as I told you, because when you have neuron, it's not one neuron. There are multiple neurons stacked across a layer. In the same line, it is stacked up one upon the other one. So in a single layer feed forward network, we'll talking about something called feed forward. Means output is not going back in any way. Of course, internally happens, but not external representation is not there for that. So such kind of networks are called feed forward. I'm just feeding it for forward direction. And single layer because there are no any other layer, just one input layer and one single layer. And finally, that is the or one layer of computing units. Basically, it's a cyclic connection. It is not going, any output is not feeding the input. This is what you mean by that. Then there is something called multi-layer feed-forward networks. When I say multi-layer feed-forward networks, so there may be one input layer or more than one input layer. So there are one input layer, of course, then we have one hidden layer, but not necessarily that hidden layer is only one. And there may be many other layers. So I'll just explain what do you mean by hidden layer. So with more hidden layers, it is possible to capture the higher order statistics and it can be extracted. So, and there is another class of network. So these are, I'm talking about very basic and general building blocks for the deep networks as well. So another is recurrent network. So when in the moment it says recurrent, so recursion, you know that something is happening. It is taking the input from the output in this one sequence, this one in that particular way. And here we have some sort of feedback loop exists. Okay. Let's see this with this some diagram. Try to understand what you mean by single layer feed forward, multi-layer, and recurrent layer. Okay, and also layers can be fully connected or partially connected. So this has to be shown. And a common notation to express a feed forward network is M, H1, H2, Q. So I'll explain what you mean by that. M indicates the number of inputs in the input layer. Remember that at this layer there is no neurons indicated. No neurons will be there. H1 indicates how many neurons in the first layer, and this is called as a hidden layer 1. H2 indicates how many neurons are there in that particular layer, and this is called hidden layer 2. And this is Q is the output layer, that it indicates the number of neurons at the output. Now, because these layers are sandwiched between the input layer and output layer, so sometimes or they are also called as a hidden layer because you are directly not interacting from the output side to this layer, so we call it a hidden layer. So we'll try to see with an example. So here if you see, this is simple layer, and remember that, and this will notation follow throughout our course. In other books or some other source, they might be using a different notation. So we'll follow. To represent the inputs only, we write small square boxes. And to represent this neuron, that is computation unit, will represent by a circle. Now don't just swap it, and many a time people will do this. Even the input also they mark circle, even though it is understood, but notation will we have already defined and should not be confused. Okay, so if you do this, you will be losing some sort of a mark for that. So be careful. Now, this is a input layer. So input layer is nothing but it indicates what are the input sources. For example, if you remember that on that day we were discussing about some example I was talking about, or let's say, okay, let me quote a very simple example here. The students when they are in Manipal and let's say they want to uh, when they move to a higher semester, that is in third semester or above. So some of them they find in hostel is very difficult life, this blah blah, we cannot come at any time if we want, etc etc, many other things. Or they cannot have a room partner what they like, they're comfortable with, so they want to move out of the hostel for whatever the reason may be, let's say. Now you want to rent a home or a house outside the campus so that you can live the life you want. And let's say you are required to design, or you want a system to be in place where you just want to give your requirement that I want a house with a 2 bedroom, so and 2 washroom. It should have parking because I want to own a bike or a car, and I am a environmental loving guy, so I need a garden, and it should not be far away from the college, even though I may not have a bike or car or whatever. It should be within a walkable distance. So these features which I'm talking about, when you see this, and once you give the specification, after this, when you press enter, the system should tell you that what is the probable rent for this, the specification which you have given it. Okay. So this scenario you remember, because we'll be using this scenario every now and then. Now let's say this input here. So when I talk about this in particular problem, this problem scenario only, let me call it as a rent prediction system. So I need to specify the number of bedrooms I'm looking for, the number of washroom it should be, right? How many washrooms should be, and whether parking is required or not, whether garden is required or not, and the walkable distance from MIT. So let's say this is the 4 inputs. So any one of these features can be the number of bedroom, washroom, walkable distance, parking, yes or no, right? So these are the different inputs, and these are the, let's say you have this kind of neuron. And here, of course, what the problem we are discussing, it has nothing to do with this kind of structure. It is completely different because it's giving 4 outputs. So, and in our problem at hand, it won't give you 4 output, it's going only 1 output, that is the predicted rent. Anyway, so this I'm just telling you that what input here it will be. Now when I say about this one, so this is called a single layer feedback, because the layer, there is only one layer and it is having 4 neurons in that. And that's why they call it a single layer feed forward network. There is also possibility that I can have a multi-layer feedback forward network. When I say multi-layer feed forward network, so what will happen? Definitely 1 or 2 hidden layer come into picture. So it can be, so let's say here I have this kind of structure. So, and this kind of connections, if I see, show here, these are called fully connected. Fully connected means this particular input goes to all the neuron in the next layer, goes to all the neurons here. This. So each input has a 4 outgoing links because of 4 neurons in the this particular layer. Each one, 2, 3, 4, like that. So this kind of system or the connection is called fully connected. And then we have this concept of partially connected. Partially connected means it does not happen in this way. Some of the connections will be disabled for many other reasons, which we'll discuss. Now, so as I told, there's a multi-layer feed-forward network or multi-layer network, or sometimes simple call is MLP. So you have this kind of this one, and now you may probably realize it. If you use the block diagram approach, even for such a small diagram with only 6 neurons, it will be very complicated unnecessarily. All those activation function indication or those weights indication, it will become very complicated to represent. Moreover, showing the weights or the activation function does not convey any major message to you. It doesn't help you in any way as far as computing is concerned, because this is implicitly very much over there and you're working. Ultimately, what is important for you, what are the input you're giving, and what is the output you are getting it. In between, you know, if you know the process, how the computation is happening. Okay. So anyway, so this is basically multi-layer, or you can say that a neural network with one hidden layer and one output layer. So this layer is hidden and it has 4 neurons and the output layer is only 2. Now the question comes, how do I know that how many hidden layers should be there and how many neurons are required in per hidden layer or output layer? So more on this in a couple of minutes. We'll discuss a few guidelines on this. And now there is another kind of network which network architecture we discuss, what is called recurrent network. So recursion is the process. If you see here, this is the output and this Z inverse, and in this particular this is basically Z inverse is a notation to say it's a delay element, means whatever is there, it will be delayed by 1 unit. So what do you mean by that delay? So delayed by it. So this is something like this. I don't know how many of you have ever studied difference equation. Have you ever come across difference equation? Not differential, difference equation. Hello? Hello? So anyway, so this, when I say this, yeah. So whenever you have something like this, and this is xn, right? So when I say this one, so it got delayed by this xn minus 1, something of that sort. That's all. Delayed by this. And if you have multiple units, accordingly, those many delays will be there. Now, what is happening here is this whatever the output is, there some sort of delay unit. It is not always standard, and it says unit time delay operators maybe more than one or whatever the requirement may be, and these are given feedback to this. So some sort of feedback. See, it is giving input to this one, and from this it is getting input from here like that. So this kind of network is called recurrent. So this is very naive representation of a recurrent network. Actually, it is very complicated just to represent this in a very basic form. So you should be you should have a clarity. What do you mean by single layer network? What do you mean by multi-layer neural network? What do you mean by recurrent network? Whatever the network which will come across, or you might see some sort of research paper they are mentioned over there. So those network structures are built upon such kind of networks. Okay. Now sizing neural networks. We'll try to understand basic sizing when means what is the number of learnable parameters, means how many parameters it is required to learn. Now in this diagram, that is figure 19, can you tell me how many neurons are there? Anyone? How many neurons are there?
So 9.
Okay. Now, just some time back, I told you that input layer will be denoted by square boxes, not by circle. But this diagram I got from somewhere. So that's why it is mentioned in a circle, everything they mentioned. And I told you that input layer, there is no neurons. No neurons in the input layer. So here, input layer, it is nothing but, you can imagine these are the square boxes only. And just to indicate that there are three input points for this, x1, x2, x3, you can say that. Is that okay? So excluding that, so we have four neuron in the hidden layer and two in the output layer. So effectively 6. Okay. So the number of neurons are 6, and of course we don't count the inputs layer. So even though if you come across some kind of diagram which they mention like this, so this one, you should not count those circles, etc., from the input layer. Okay. Now, can you tell me basically what is happening that here? Okay, let me just use a diagram just to get an idea how things will happen. A simple diagram, let's say I'm going to draw the architecture for 3, 4, let's say 2, same whatever is given in this particular. So I have this kind of point, let me say, and I'm some sort of this x1, x2, x3, whatever these features may be. Let's not about that. You have this maybe, and then we have this. Some of you have switch on your microphone. Please switch it off or mute yourself. So this we have, because it is going to be fully connected. So you have this, and we have this, right? So I just wanted to tell you the weights, how we go about writing these weights. Okay. And if I write all the weight, it will be very complicated. But still, let's do this. So let me call this neuron 1, 2, 3, 4. So neuron 1 is connected to this x1, and just to indicate this is a synaptic weight, I'll mark as a W11. Remember that we used to say KJ. So this indicates the neuron and this indicates the input. Okay. So likewise, this if I write, it will be W12 and this will be accordingly W13. This part, this one, what should it be? W21. Accordingly, this should be W22 and this one is W23. Similarly, I can mark this one accordingly W41, W42, W43, right? So all these things are there. Now the question is, these many parameters are there. Similarly, we'll have this kind of connection as well. And this you can mark it as a also, let's say, AB. So this I can say WA1 and this I can say WB1. Similarly, I could have mentioned like this. Okay, so if I want to mark this, this will be WB4, this will be WA4, likewise. Okay. Now, when you see this kind of some sort of connection is there. These are the matrices effectively. So some matrix formation will happen because what is happening here, if you remember that we discussed something called activation potential. So and when what is not marked here is something called bias. Bias we have not marked. So remember that when to mark bias, we always say that bias is x0, which is marked as a or equal to +1, and it is connected to this. So this one basically B1. That will be the weight. To indicate that the entire part, we say I equal to 0 to m, and we say w. If I want to say j, I can say j w k j x j. So this is the input which you are getting it, and let me call as a potential activation potential for neuron 1. I can mark it as a 1, not a problem. Suppose if I do this, so we can write like this. Whatever the equation here you get it. Means what will be this particular output? The output of this one. So this will be nothing but let me call it a V1. That is the activation potential for neuron 1. So that is your W10 X0 plus W11 X1 plus W12 X2 plus W13 X3. When I write this, everything, all these weights are taken into account which are getting input to here. Okay. Finally, the output of this one will be nothing but phi. If I want to name it as a y1, y1 will be nothing but phi p1. Right? So this is all. So this is for one particular neuron. So we want to have a matrix like this, matrix like this. So in that case, forget about this for the timing. I'm talking about this kind of matrix. So we have V2. Similarly, I can get it. Remember this 1, 0 is indicating the input coming to the neuron 1 and taken input from the 0th. For the bias, in order to take into account bias, we marked as x0, which always fixed at +1. So I can write this one as a W20 x0 plus W21 x1 plus, and let's say W23 x3. Likewise, I can have for V3 as well. So V3, I can also have this V30 x0 plus V31 x1 plus V33 x3. Now, when you write this equation, is it possible to write such equation in matrix form? Can we do so? Hello? Can we do so? Yes or
Yes.
no? Yeah, we
Yes.
can. So when we do this, which you have done in school very early, so 10 W11 W12 W13 20 W21 22 23 30 31 32 33. When we have something of this form, and of course these inputs will be there x0, x1, x2, and x3, etc. So this particular part will be called as a weight matrix. Weight matrix. And the dimension of this weight matrix, as you can see, it is 3 cross 4. Okay, 3 cross 4. Now, why I said this in all this detail, because this in books and all, sometimes directly they write it. So remember that the weights corresponding to the first hidden layer is nothing but how many input it is coming. So that indicates the number of rows, and number of neurons in that particular layer is indicating the number of columns. So basically rows and column, right? Right here at this thing, now you can say that what will be the matrix size? Matrix size will be 4 cross 2. Likewise, we'll be doing with this. We'll go for this one. Mm, uh, okay, yeah. So here we know how many learnable parameters are. Learnable parameters in a neural network. So far you have seen. What are the learnable parameters? What are the learnable parameters over here? Any idea? Anyone? Hello. Okay. So learnable parameters are here nothing but your synaptic weights. So weights are the learning parameters. So as last class we discussed, the knowledge acquired is stored in terms of in the synapses itself in terms of weights. So those are the learnable parameters. So we wanted to know for a simple this kind of architecture how many learnable parameters are there. So we found this many neurons are there. So first we'll find the learnable parameters from the hidden layer so here because input layers are three, so we just mentioned 3 into 4, but here example which I mentioned here is I wrote here basically this 3 cross 4 is happening due to this particular part of it. Okay, fine. mm, okay. So we'll see that this becomes also 3 cross 4, so the weights are 3 cross 4 plus weight of this layer, that is 4 cross 2, 4 cross 2, and that is 20. Apart from this, one of each of the neuron has got one weight. This has got one weight, and that particular weight has to be not weight, what we call the bias. So how many, the number of bias variable will be equal to the number of neurons. So there are 6 neurons, so there will be 6 bias. So we'll be adding it. So bias will be basically 6. So the total number of learnable parameters are 26 in this, right? So likewise, you can expect that, okay, a random architecture is given to you and you are asked to find how many learnable parameters are there in this particular network architecture. That's as simple as that. So, and to give an idea that some sort of context, the modern CNN contains on order of 100 million parameters. You can imagine 100 million parameters and are usually made up of approximately 10 to 20 layers, and each layer will have hundreds of neurons. So you can imagine that's why the complex it is so complex and it takes a lot of time to compute, and that's why people will look for some sort of GPU based system to train the neural, and that's why they call it deep learning, because normally it is quite deep. Sometimes this they draw it like this in a, you can just flip this so that this becomes top and this becomes down, and that's why when you increase the number of layers it goes quite deep. Probably from that way they use this name deep learning. Now we'll try to understand few guidelines, I would say, not the hard or explicit information, rather it is more of empirical in nature, that how do you decide this neural networks, how do you design for this. So first of all, we select the architecture and gather input samples and train using a learning algorithm. So that is the learning phase. First we decide what kind of learning algorithm we are going to apply. Okay. Then we test with the data not seen before. That is the generalization phase. When I see generalization, can anyone of you tell me what do you mean by generalization of an algorithm as far as learning is concerned? Anyone? Can you tell me what do you mean by generalization? Are you there?
So generalization in the sense the model has to work for all kinds of data specific to the task at hand.
Okay, okay. So generalization, basically what we mean by that, like, okay, let me give a simple example. Let's say in class, we are studying a lot of differential calculus or integral calculus problem. And in exam, you may not expect that same problem will be asked to you. So any problem will be given to you now because based on your learning is so generalized, means you learn so well that a problem which is not part of your training or testing, if that is given to you, you are able to solve it. That is called generalization. And how fair you or well you are doing on those data which not seen before is going to indicate the generalization capability or the learned performance of that particular system. This is what they mean by generalization phase. So that's why they say test the data not seen before, means it's not part of training. And also, first of all, any sort of neural network design, when you say it's basically data driven, unlike conventional programming. Here, that's what I say in machine learning neural network, that we don't have to explicitly program for the each and every changing data. Let the data will dictate how the system will behave. So model will change accordingly. Now, before this, we'll go for this particular part, that how do we decide on what architect to use when faced with a practical problem. We'll see that problem scenario only indicate that what should the architecture to choose. And second is, I don't know, this point I forgot to go for one by one. Anyway, should we use no hidden layers, one hidden layer or two hidden layer? That is also decided by the problem at hand and certain other experience you must be having. Also, how large should each layer be? When I say how large each layer should be, literally what I mean to say, how many numbers of neurons are there. So some of the things is clearly decided, it can be identified clearly. Some, of course, based on experience, you will come to know, and based on the problem at hand. But here, remember that as we increase the size and number of layers, when I say size means the number of neuron in a particular layer, and the number of layers neural network, the capacity of the network increases. Now, what do you mean by capacity? I'll just explain with the diagram also. But here we just see that capacity means the space of representable function grows since the neurons can collaborate to express many different functions. So you have one neuron system, two neuron system. So what do you mean to say that as you increase the number of neurons, so the kind of function it can approximate also increases. This is what you mean by capacity. But the question is, should I keep on increasing? Should I keep on adding those neurons in order to find that? No, because there is some limit for this. Otherwise, you'll be unnecessary doing this computation, and it does not yield anything to your problem as far as accuracy or efficiency is concerned. So we'll see. So here, if you see that the same kind of data is there, same kind of data here in all the three, this one. So in this, and of course, this are binary label data, let's see. So you have green and red, green, red, green, red. And if you see this in this diagram, only 3 hidden neurons are there. And for whatever the output, you can say, of course, 2 neurons, because for one for red, one for green. And the kind of boundary it is creating to inclusion of for the inclusion of all this red dotted values is of this fashion. And you can see clearly that it is missing this, and this data, which should be also part of this particular boundary, but it is missing it completely. So it is not able to approximate the function which is generating such kind of data. You can see that. When I add the more number of neurons, so and suppose it is become 6 hidden neurons are there. So you can see that now the function has taken a different shape altogether, and it has taken some other point into account as well. But still, there are some points which is not part of this kind of class, this class. So it has not really learned that way. So all this overfitting, underfitting, those stories we'll see later. For the timing, just confined to this, that what do you mean by learning capacity? Now, from this, people have gone to this kind of neuron. Let's say 20 hidden neurons are there. And if you see in this, what is happening that almost all your function is approximately so well that it has covered the entire red component. There is no red component which is not part of this kind of zoning process. So of course we have something to compromise, but for the time being, you just understand that as we increase the size, the capacity of the network to learn more and more variety of functions are increasing as well. So here, if you see, the structure of the boundary is different. Here you see structure is different. Here it is completely different altogether. But then, but you should not be under the impression that I should keep on increasing. There is a limit for that. And of course, you have to visualize the things as well. Simply blindly, you cannot keep on increasing. Sometimes it is quite empirical in nature, but this is how it works. Any question here? Hello? Okay. So this is how we go about it. Now the question is, as I told you, how to choose the architecture is most of the time some sort of problem will be specified to you. So problem specification helps define the network in the following ways. First, find the number of network inputs. So the number of network inputs equal to the number of problem inputs. Now, if you remember that I just now, some time back, I quoted one problem scenario, which is called a rent prediction system. Let's say you are required to design a rent prediction system. So how many number of inputs are there in that? Hello? How many number of inputs are there? Basically, there are 5 number of inputs. So one is your number of bedroom, number of washrooms, and you can say that the parking space is there or not there, garden is there or not there, and then walkable distance to MIT. So these are the 5 input variables. So number of inputs equal to 5 in this particular case. The number of neurons in the output layer equal to the number of problem output. In this problem, whatever we have is just one output problem. So only one neuron is output is enough because we just wanted to know the rent. Let's say there is some other system which we want another features as well. So something, the number of neurons in the output layer will go up again in that case. The output layer transfer function choice is partly determined by the problem specification of the output, as is mentioned, partly, not solely. So we'll see that how to use this. Now here is a problem for you. An example is that a single layer neural network is to have 6 inputs, 2 output, 6 inputs, 2 outputs. The outputs are to be limited to and continuous over the range 0 to 1. Continuous over 0 to 1. What can you tell about the network architecture? Specifically, how many neurons are required? What are the dimensions of the weight matrix? And what kind of transfer function could be used? Now, please let me know, any one of you. How many neurons are there?
So 2 neurons.
Okay.
That is because it should be a single layer neural network. So the input, we have 6 inputs, and the output will have 2 outputs which are required. And since the output is in the range of 0 to 1, we'll probably use the sigmoid function, and
Yes.
the dimension of the weight matrix will be number of inputs will be 6 cross 2.
Yes, perfect. Any information do you have about the hidden layer in this particular problem?
No, sir.
No. Yeah. So whatever whoever said this is perfectly correct. So first of all, it's saying that single layer. So the moment you say single layer, so there is no question of hidden layer. Okay, there's no question of putting hidden layer. There are 6 inputs and 2 outputs. So definitely 6 inputs means 6 input variables will be there and 2 outputs. The moment I say 2 outputs means 2 neurons at the output layer. So that is basically 2 neurons. And how many neurons are required? Only 2. And what are the dimension of the weight matrix? So basically 6 inputs and 2 outputs is 6 cross 2 is the dimension of the weight matrix. And what kind of transfer function could be used? Because it's 0 to 1, so as he pointed very correctly, so we may go for this sigmoid. Okay. And is bias required? If somebody says bias required, no idea. First of all, I'll tell you that if bias is not mentioned and if you try to compute it automatically also, there's no harm in that, right? But in this particular problem, there is no information about the bias, whether bias is required or not. Remember that last class I discussed in length. What do you mean by bias? How do I know that I have to apply bias in general? And but in the neural network, we take by default, we put a variable and let it learn. Means if there's some sort of bias in the data, let it learn its own. So good. Now we talk about something called knowledge representation. Now, knowledge, which we referred in the starting, the definition of the neuron, is very vague. We said the knowledge it acquired, etc. But what do you mean by that? How does it happen? What is the representation, etc.? We didn't bother about that. So today we'll just try to explicitly ponder over those points to some extent. So knowledge refers to stored information or models used by a person or a machine. You can see, remember that. Stored information used by a model or a person, sorry, a machine to interpret, predict, and appropriately respond to the outside world, right? So if you remember that, uh, we discussed last class something called passing through the Nagabana road here. And I put the scenario that let's say once it so happened that you are passing around 8 o'clock and you are alone and your phone was snatched. Let's say this is a bad scenario to quote in Manipal. It never happens, but let's say, imagine. This is I'm putting because this is the only scenario we can all can correlate. And so it says that knowledge refers to that models used by person or a machine to interpret, predict, and appropriately respond to the outside world. So suppose you have come across this kind of scenario and bad experience definitely, and this is deeply ingrained in your brain, and you know that okay, man, I'm not going to walk through this particular way after 8 o'clock or so, or you can say that after sunset, I'm not going to pass through. This is not a safe passage or place to go. Rather, I'll take a main road from MIT inside campus. And using that particular information, now new scenario when comes, so you're able to predict. Able to predict means today I'm late around 8:30 or so. Once it has happened to me around 7:30 or 8 o'clock means after sunset. So you predict chances are there my mobile will be snatched again if I pass through this particular passage. And appropriately respond to the outside world. So appropriately means based on your prior experience or the knowledge which you acquired based on prior experience, you are just invoking those experiences and now you respond to the outside world, means what you should do in this current scenario. So this is what you mean by it. Now its knowledge can have many ways, but it's basically what information is actually made explicit. It depends on two factors. One is this one. Second is how information is physically encoded for frequent use, subsequent use, means how, means in what way it is encoding is done so that it can be used further. So we'll see. These are the two factors on which the knowledge basically depends or it is represented. So knowledge of the world consists of two kinds of information. A known world state means what is and what has been known. So that is prior information, some sort of. Another is observation or the measurement of the world obtained by sensors. They can noisy. They provide samples. Examples can be labeled or unlabeled. So this is the observation. So this normally happens in case of machine learning or neural network. Now there are certain rules for this knowledge representation. And first of them is you can say similar inputs from similar classes should produce similar representation inside the network and should be classified into the same category. And don't you think so? We do in our society also something like that. Like you, let's say uh, you are in class. I'm talking about in school happens a lot, and you are a good performer most of the time. And there are a segment of students who will be a bad performer or poor performer. and once or twice, two unit tests you gone down, and then your teacher tells you, तुम भी उनकी तरह होते जा रहे हो. So what they mean to say implicitly that some sort of similarity measure they are trying to attach you with the other kind of pattern, right? So this kind of similarity measures. So can you tell me few similarity measures which you come across, which you use for the data to represent uh, one vector or one variable with another? Can you recall few similarity measures? Anyone of you? Okay, so we will see here one simple thing. So I'll just go to board and I'll tell you a very simple one which we normally come across, and it's quite oftenly we use. I need another page. So let me. Okay. So let's say I'm having a vector x, and it is of type this one. Okay. The moment I say this, what do you mean by that? How do you mentally interpret it? How do you mentally interpret it? Any one of you? Okay, so this is XRM, which is literally mean to say that X is something like here. You can say one component, one. If I'm saying this one, so one, two, dot, 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 X1M. Basically, it's a vector, m-dimensional vector. But normally in books or research papers, we don't represent like this. So rather we always write like this: x11, x12, x1m, and t, just to sake of. But whenever you come across this kind of this one, you see that is an m-dimensional vector. As simple as that. Okay. Now, before I go for this, so in order to differentiate two vectors, let me say xi and say xj, two vectors, and then I want to find the Euclidean distance between the two, because you remember that Euclidean distance is the first kind of similarity measure. This is which we have studied something called in coordinate geometry in schools we have learned, right? But of course in coordinate geometry we were only talking about the two dimensional, but in Euclidean space we have n dimensions, so that's what we do. Okay, and then we have this am I audible to you? Hello?
Yes, sir.
Hello? Am I audible?
Yes, sir.
Sir, you're audible.
Hello? Am I audible now?
Yes, sir.
Okay. There was a signal drop. That's why I asked. Okay, fine. So let's say these two things are there, and of course both of them are of this form. Means they are uh, m-dimensional, and we want to find a Euclidean distance between the two. So for this, let me say I'm representing this by xi, xj, which I can represent by xi minus xj, right? So this is, sometime you write here subscript, but when you say this, it is always implied almost. So when you see this, so we Literally what we mean to say is something like this. Let me call as a k equal to 1 and here m, because dimension of both the vectors are equal to m. And here I'm talking about the first vector, kth element, minus second vector, kth element. So element by element difference, we take it, find the square, and take the root. This is what we do. And this kind of thing, what we call this as a Euclidean distance, right? And the lesser the Euclidean distance, smaller the components are there. If it is equal to 0, means you're talking about both the data are same, right? So this is what is happening. So Euclidean distance is one of the similarity measure, but this is not the only one. One often uses another similarity measure, and that is a cosine similarity or something what we call inner product. So in book, Simon Haken, he talks about xi as a xj, this as a similarity, cosine similarity or inner product. Instead of this, which is not very universal in nature, we'll be using this notation. This was there in my slide also, and linear algebra probably, xi comma xj, which is nothing but xit xj. So this is basically it is what is happening that um, is it's inner product, as simple as that, inner product. And we know that this is equal to, if of course is m dimension, so I can mention this without any problem, k equal to 1 to say m. This xi, remember this xi is nothing to do with the index, it's just indicating the identity of the identity of the vector we are using it. So I can say xi k and xjk, right? So this is just competition of that. Now we know that cosine similar inner product, or on our inner product we always define in terms of cosine similarity. So we say that something like this. If this is xi, this is xj, and this is the angle of theta, and effectively this point is nothing but the projection of xj on xi, right? So this, whatever you compute, is nothing but xit xj. Not necessarily always write xit xj. I can say xjt xi also. Okay. So this is what is happening. So this is inner product we found. And if I connect this two, so basically you are finding this as a, this is nothing but your xi minus xj or xj minus xi, doesn't matter. So this is nothing but your Euclidean distance. This you are finding a Euclidean distance. Okay. Now, why I'm saying this, and there's something to do. I want to correlate the two. Euclidean distance is also a measure of similarity, but here I'll say that, let me take two elements, three elements, x1, x2, and x3. And I say x1, comma x2 is say some 3, something, forget about the unit and all. And another is 3x1, x2 equal to 1, right? Now the question is, x1 is similar to x. Sorry, I did a mistake here. X1 is similar to what? More similar to which particular another vector? X2 or x3?
x3, sir.
X3. So this is a simple thing. We are having understanding that Euclidean distance, if it is lesser the Euclidean distance, more the similarity between the two. Now, in case of inner product, the things is quite different. Here, If xi, because theta is, we know that this particular thing which inner product is normally written as cos theta xit xj over the amplitude individual, right? So this can have a maximum value of how much it can have maximum value 1. It can have maximum value 1. And that will happen only when theta is 0. Theta is 0 means this xi is nothing but the xj itself. That's why we can say it's similar. If I say the cosine similarity between the two vector here, if I say, let me say it's the cosine similarity, I'm just writing it across. Simply say x1 and x2 is say 0.6. Remember that it cannot be more than 1, and x1 x3 equal to, let's say, 0.9. Now what we see about this, it is similar to what? X1 is similar to what? Anybody? Or maybe I could not make you understand. So remember that inner product means higher the value, means remember that here maximum value could be 1. Higher the value, more the similarity. So, and here it is between x1 and x2 it is 0.6. Here between x1 and x is 0.9, means x1 is more similar to x3 as compared to x2. This is what I mean to say. If both of them are similarity measured, is there any connection between the two? And answer is very much yes. We can see this diagram. And this, if I project on it, this is basically this gives the inner product, and the distance between this is nothing but Euclidean distance. So what is the connection between the two? If you see that the definition of Euclidean distance and the inner product, their requirements are complementary, or you can say contradictory. One is when lesser is there, then similarity is good. One is saying if the value is high, then similarity is good. So let's try to see mathematically and prove it. Is it possible? But in order to do so, let me assume normalize my vectors. When I say normalize my vectors, by assuming that the amplitude of xi and xj equal to 1. That assumption I'm making it. Now, because, and instead of writing here, I'm just writing dij, which we represented as a xi minus xj, like this, right? Or I can say dij square equal to xi minus xj square. And this, you remember, I told you that whenever there is, I can write it as a xdx. You remember? I said this in my linear algebra class as well. And the region I have shown there also. I expanded this and expanded and shown. But anyway, now here we go. So here, what do you mean to say xi minus xj t from that particular definition only? I'm saying I can say because like this. That's why. And xi minus xj, we have this. Now we'll just open it up. So we'll take t inside. When we take t inside, so nothing to worry as such because there's no multiplication, so it will remain same. Xjt transpose of individuals, and when we have this, so we can just keep on multiplying in a conventional way. I can say this xi I and xit xj, and then minus to this multiplication happens. So let me say xjt xi. Remember that you cannot switch the position of transpose, otherwise it will become outer product, and that will be wrong. And this minus becomes plus. So we have xjt, xj, right? Now xit and xi is become basically xi square, basically xi square. So here, when it's a square, so the value will be 1, right? This will be 1 minus xi xj. Let it be xit xj. Here xjt xi was there in order to just make the same thing. Either I could have swapped this or swapped that, doesn't matter. So the moment I say xj xit, in terms of this, I'll write xit xj plus xj xat. So this becomes basically the amplitude square. It will become, right, from this definition. It will this one square. The value is, anyway, we have already written that it is normalized to 1, so it will be 1. So what I can say here, 1 plus 1 2, so 2 minus, this is also 1 and 1 2, 2 xit xg, and this is my dij square. So I can state one statement here. I'll explain now. Now, for dij to be minimal, what should happen to this one? This we say inner product. So inner product has to be maximal. It should be going, because this you want to be minimal. Minimal means this subtraction should be maximum, so that this overall value comes out to be lesser, right? And the vice versa we can say. So I can say that minimization of Euclidean distance is corresponds to maximization of the inner product. Okay, this relation you understand. Any doubt here? Anybody? Hello? Does anyone of you any doubt here? No doubt. You guys are classy, man. So good. Now the question why I said this thing here, because I want to talk about the similarity thing. The similar classes, similar input from similar classes should produce the similar representation, means vector wise, and that's why should be classified into the same category. So the similarity things will come into picture later, and that will be measured in terms of Euclidean norm, Euclidean distance, or the cosine inner product. Another rule is that item to be categorized as separate classes should be given a widely different representation in the network. So it's quite obvious, and some related readings are there. Please do it. It's quite theoretical in nature. Also, if a particular feature is important, then there should be a large number of neurons involved in the representation of that item in the network. So remember that. Something more important is that the more number of neurons are required to go for that kind of representation. Also, the last one, rules of the knowledge representation, is that prior information and invariances should be built in the design of a neural network. Somehow it should be incorporated, thereby simplifying the network design by not having to learn them. Now, some sort of invariances and prior information is there, so you don't have to learn them. So this should be incorporated. So effectively, many of you must be aware of there is something nowadays called transfer learning. So let's say you have done some sort of, somebody has trained their network on the MNIST data set. So they don't want to, and they want their some sort of number recognition only. Let's say MNIST is basically 0 to 10, 0 to 9, there's number representation and recognition. So if model has been trained on that and you want a system to be designed, let's say postal code scanning you do, and you want this pin number from the packages or envelope to be extracted. So in that case, you don't have to scan all kind of pin numbers from the different envelopes, create a data set and design your own networks. No need. Use the MNIST data set, which is somebody has already used and trained their model. So directly you can use the model and just incorporate it in your design. It will work well. So some sort of a prior information or can be incorporated. So this is one of the example of prior. More on this we'll see. Now the question is, how do I go for building prior information to neural network design? So currently there are, as they mentioned very clearly, there are no well-defined rules for doing this. We have some ad hoc procedure that are known to give a good results, as is mentioned, ad hoc procedure. So, but I told you this transfer learning, which is very much in demand now and frequently used. So, but from a classical perspective, this is how it goes, that we can go for restricting the network architecture through the use of local connection known as the receptive fields. So here it is mentioned that what do you mean by receptive fields? So, and receptive fields varies in what context you're talking about. So it mentioned that in the context of visual system, the receptive field of a neuron refers to the restricted area on the retinal surface, which influences the discharge of that particular neuron due to light, means at what time and due to what reason that neuron will be activated. So that is the receptive field. Now also there is a possibility that you constrain the choice of synaptic weight through the use of weight sharing. So some weights are shared now. So we are constraining that this value has to be taken only in this. But you can say, can we decide it off the shelf that value should be confined to this much for this particular weight? Of course, empirically it has to be come to that particular conclusion, not directly. And when I say weight sharing, so when I say weight sharing, so what will happen that other we don't have to learn again. So this is how some sort of prior information you are incorporating it. So due to the second point, this one, the number of free parameters in the network is reduced significantly. And remember this, whenever this word comes free parameters or degree of freedom. So this literally means the number of variables. Simple. No need to get confused. When I say free parameters, what I'm trying to say that, let's say in your network toy type network which we discussed earlier, and it is some, let's say 20 parameters are there. Out of 20, actually, let's say 5 weights are fixed or you are constraining them, and that are shared accordingly. So those repercussions will happen, and the number of learning parameter will reduce, which is much lesser than 15. You don't have to learn those things, or much lesser than 20. So this is what you mean to say that the number of free parameters in the network is reduced significantly. This is what I mean to say. So this is how example they want to say that, illustrating the combined use of receptive field and weight sharing. Weight sharing this, so you see that this is not a fully connected network. If you see, like say first point is connected to only this one, second point only this and this, third point has only 2 outputs, and some have 3. So there is no common this one, and some sort of weight sharing is also there. Whereas at this particular layer, it is fully connected, but this layer is not fully connected. So this kind of way, it is possible to incorporate the prior information. So it's a restricted architecture by construction, and 6 source nodes constitute the receptive field for the hidden neuron, and so on. For this one only, the constructive, the receptive field for this only. And weight sharing, constraining, constant when say use same set of synaptic weights for each neuron in the hidden layer. Same set of weights. You're not changing anything. So we may express this induced local field of the hidden neuron, this one, as something like this. So this particular formula they have used, or the kind of architecture. So before directly drawing the architecture, first people try to come out with the formula. What is the mechanism I'll be using it? And this is how they're done. Now, and this is something what happens in convolution network. So convolution layer happens, it is not fully connected. So basically there is a definition itself, what is called convolution. So convolution have this particular, it is more fundamentally taken from the signal processing community. And you might have seen convolution in your communication theory classes as well. But this is how some sort of convolution network work in this way. Now, when you go for this, I'll give you another 2 minutes. I'll just wind up this. So how do I build invariances into neural network? So there is invariance by structure that is also possible, and invariance by training also. And finally, this invariant feature space also. So this is how it can be done, these 2 things. Just read a little structure about all this invariance incorporation. It's a more theoretical in nature, just read it. Here is, I'm just giving a quick example that what is happening here. So example of logistic function, or let's say forget about whatever function is there, which you are named as a logistic function 1 over 1 plus e to the power minus ev, whose limiting the values are 0 and 1. Basically, it is nothing but a sigmoid function. Now the question is, what is the value of slope at the origin? If this the question comes, what you're supposed to do? How do you find the slope at the origin? For slope, what you do? Any function is given to you and you are asked to find the slope. What do you do?
So differentiate.
Yes. So in this case also you differentiate and find the value of that particular differentiation at origin, means at v equal to 0, because a is, you know, that is a constant, and whatever the value comes out to be, that will be slope, right? So another example here is a neuron, let's say J, receives inputs from 4 other neurons whose activity levels are. When I say activity levels are, means this is the value you are getting it. The respective synaptic weights of the neurons J are this, means these are the inputs and these are the synaptic weights. Calculate the output of the neuron J for the following situation. Situation is, you can say that what is happening, that neuron is linear. The moment that when I say neuron is linear, means activation function is linear, means whatever activation potential, output remains same. So what you do, that 10 into 0.8 and minus 20 into 0.2 plus 4 into minus 1 minus 2 into minus, because these are the x and these are the weights. Just keep on multiplying, and whatever the value comes, that is the activation potential. Now if this activation potential is given to the neuron and the neuron is linear, the same value will be at the output. Okay. Now another situation is that the neuron is restricted by a Michaelis-Witz model. So assume that there is no bias applied to this neuron. So in this case, what will be the output? Roughly, rough guess. Anybody? So whatever the activation potential you have computed, and remember that Michaelis-Witz model use thresholding function. It means that if the value is greater than 0, then the value is output is 1. If the value is less than 0, then it is 0. So whatever the value of activation function you compute, it depends on that, and accordingly the value will be either 0 and 1. So I'll stop here, and we'll see more of our learning outcome and learning processes, etc. later. And just a minute, and